So the next talk is going to be given by Kathleen Mandt from Johns Hopkins Applied Physical Laboratory, talking about the potential exogenic origin for volatiles sampled by the LCROSS impactor. So I will let Kathy take over.
Okay, thank you. Can you hear me very well?
Yes, we can.
Okay, good. And can everybody see my screen? The presentation.
Yeah, you're good.
Okay, good. This is the first time I've shared a screen with Teams, so I was a little bit nervous that it wouldn't work. I want to thank the organizers for giving us the opportunity to share this work, and I'm really excited to be part of this session on science on the moon. And a lot of the other presentations are also relevant to this. This paper was recently published in Nature Communications, and I'm going to go over the results and then talk a little bit about the implications for the VIPER mission and what we can do with that data. So the LCROSS plume, or the LCROSS impact, took place in 2010 as part of an experiment to look at volatiles and directly sample the volatiles that are in the permanently shaded regions of the moon. It impacted Cabeus, and it sampled not only water, which pretty much has been what we've been limited to observe with remote sensing so far, but it also observed carbon, nitrogen, and sulfur-bearing volatiles, which was an important first measurement, and I'm looking forward to future measurements like this as well. Now, it's been 12 years since that impact took place, and we've had some studies trying to look at the origin of those volatiles, but this is an inherently challenging process to take these measurements that are made in the PSR and trace it back to the sources of the volatiles. I show on the left of this figure the volatile sources that we've identified as potential sources for volatiles that are in the permanently shaded regions. There's volcanic sources or endogenic. That's coming from the historic time periods on the moon where volcanic activity was occurring, and there was a lot of outgassing from the interior. The endogenic sources are cometary, asteroid, micrometeorites, and solar wind. The problem is that we have a lot of things that happen to these sources when they're delivered to the surface of the moon between that delivery and deposition and storage in the permanently shaded region. And these processes are extremely complex, and what makes it really difficult is that we don't know the rates at which these processes are taking place. So it is very difficult to take the composition that we measure in a permanently shaded region and trace it back to its sources. But it is not impossible. And we found a way to simplify these processes without having to know the rates by going with the elemental ratios instead of the molecular composition of the plume that was measured and what we know about the molecular composition of the sources. So what we did was we took what we know about the composition and turned it into elemental ratios of nitrogen, oxygen, hydrogen, and sulfur as it related to the carbon that is in the sources and is in the plumes, and compared them to each other. So this eliminated any chemistry that takes place in these processes shown on the previous slide, and helps us to also reduce the effects of any rates possibly that are taking place that change the ratios. Now, so this figure shows a summary of the elemental composition of the plume, which is shown in black. And we have two composition interpretations of the LCROSS plume, depending on the type of ice that is storing these volatiles in the permanently shaded region. If the volatiles are condensed onto the surface directly or onto the regolith grains, then they would be condensates. And they would be released into the LCROSS plume based on their volatility temperature. So the more volatile species like carbon monoxide would be released from a larger area of regolith as the regolith is heated by the impact that caused the plume. Then, whereas water, which has a higher volatility temperature would not be released from as large of an area as carbon monoxide because it's not quite as volatile as carbon monoxide. So the condensate composition takes that into account and assumes that the volatiles are directly condensed onto the regolith grains. In the case of storage in clathrates, these are water cages that trap molecules inside of them. And when a clathrate is storing volatiles and then is destabilized and releases the volatiles into a plume, everything would be released at once. So we can interpret if the volatiles are stored as clathrates, then what we see in the plume represents what was in the regolith in the permanently shaded region. So we took into account the type of storage of the ices, and then we compared that to the different volatile sources. What you can see from this figure is that no single individual source is able to explain the composition in the plume because you have differences in nitrogen compared to sulfur. And so there's no single source that falls within the error bars of what was measured. This means we did have to do some modeling. The approach that we took to modeling was we did a grid search for the best parameters, taking a fraction of each of the sources, and tested 167,000 possible combinations of these sources at about a 1% or more of each, summing up to 100%. We looked at 6 different scenarios, and I'm going to walk through each of those scenarios and the results from those. So these are the constraints that we set for the scenarios model. The way that we did this is because we don't know the rates that are taking place for things like volcanic outgassing, adding material to the atmosphere of the moon and potentially to the permanently shaded regions. We don't know the escape rates of material from the atmosphere. There have been papers published recently showing how difficult it really is to estimate the historic escape rate of any atmosphere on the moon. We looked at clathrate formation, sublimation, and recondensation that could affect the elemental ratios, and then we combined escape, sublimation, and recondensation. And so walking through the results, when we looked at no fractionation, assuming that what was delivered to the moon ended up in the permanently shaded regions, we found that no combination of sources was able to fit both the sulfur and the nitrogen relationship to carbon in the LCROSS plume within the error bars. There's just too much nitrogen relative to carbon and too much sulfur relative to carbon for any combination of sources to do this. So there has to be some sort of fractionation between delivery of the volatiles and storage in the permanently shaded region. We looked at volcanic atmospheric processes that included the removal of sulfur onto the surface as elemental sulfur and then escape of different species from the atmosphere. And we found that it was impossible to have any volcanic contribution at all to the material that was observed in the LCROSS plume because there's just too much nitrogen in the LCROSS plume for volcanoes to have contributed any sort of volatile contribution to what was there. So the implications of this means that the area that was sampled by the LCROSS plume, which is the top 1 to 3 meters of the Cabeus crater, has no volcanic material in it. And if we want to search for any volcanic material, we may have to dig deeper or we may have to look elsewhere, but there's just no volcanic material there. When we looked at impacts of comets and asteroids and then the escape processes and loss of some volatiles to space, we found that a combination of cometary ice and solar wind would fit the observations. So we finally had something that worked in this case. When we looked at clathrate formation, what's most important is the amount of water available to form the cages to trap the other material that's in there. And we found that the balance between the amount of water that was needed to form these clathrate cages was not really appropriate for what was observed. So with that, we were able to rule out any sort of clathrate storage for the volatiles that were sampled. So that means the same as the volcanic implications, that top 3 meters does not have volatiles the majority of the volatiles stored in clathrates. They are stored in condensates, or material just condensed to the regolith. We looked at sublimation and recondensation, and in this one, we added some additional elemental ratios to help us provide better constraints on the results. And we found in that a mixture of comets and chondrites was able to provide a pretty good fit to the observations that were made in the LCROSS plume. Now, the implications of that are that you can explain this with just comets, because comets are a mixture of ice and dirt or chondritic material. So a single or a bunch of comets impacting the moon and then adding these volatiles to the permanently shaded regions could explain that with sublimation and recondensation. We added escape to this, and we combined all three of these processes and found that comets and chondrites, a mixture of those, which could be just comets alone, ends up explaining things really well. Applications to VIPER data, we'll be getting in situ measurements of the composition, so we'll be able to apply this process to those measurements and look at the sources of the volatiles that VIPER is sampling. And so that'll be the science objectives. We'll be able to get even more measurements, get some noble gases and some isotope ratios. And that is the end. I can take your questions.
Fantastic. I think we still have a couple of minutes if people want to ask questions. I can see Mahesh has popped straight up there, so go ahead, Mahesh.
Great talk, Kathleen. You know, I can't imagine how much work you needed to do to find all those permutation and combinations. But for me, that volcanic outgassing one kind of stood out as a sore thumb. You could just rule it out. At the same time, I think yesterday I stumbled upon this paper that just got published in Planetary Science Journal. And its topic is polarized accumulation from volcanically induced transient atmosphere on the moon. And have you seen this?
Yeah.
I mean, this is claiming
I have not, but...
Okay, I will put a link in the chat box. But basically, the summary of this work is that there could be a great quantity of water ice within the first 10 meters in the polar regions of the moon. And I'm just wondering what you just, presented to us.
Yeah. That's really interesting, and I look forward to reading that paper. I think we can definitely rule out the top 1, maybe 3 meters of Cabeus crater, because that's the only area that we have sampled the composition beyond water. But that doesn't rule out deeper volatiles coming from volcanic material. It could be that comets and endogenic sources have overwhelmed any volcanic contribution in that top few meters. So there's still quite a bit to learn from the volatiles that are in the permanently shaded regions of the moon.
Yeah.
And I look forward to future exploration.
Yeah. It just beautifully demonstrates that how difficult it is to take measurement from one place like Cabeus and then apply it throughout, or vice versa, that what modeling doesn't necessarily mean what is in reality. So we've got a huge amount of work to be done, but I'm just in awe of what you were able to do. So thank you.
This is a really quick question, or a couple of questions from Katie and Roman. I don't know, very quickly, Kathy. Katie's asking, are you able to tell much about the type of carbonaceous material, whether it's CI, CM-like, or like rather than ordinary chondrite or carbonaceous chondrite?
Yes. Where we used CI and CN for this analysis, we didn't go any more in depth than other types of carbonaceous chondrites, and we could probably add that to the model and constrain limits on percentages for each of the types of chondrites, and that would be some interesting work to add to this.
Sounds good.